After previous videos, we have prepared inputs for encoder and decoder. And if we look at the diagram, it would be these in the diagram. You pass inputs, you embed it, and you add positional encoding to that embedded tokens. And same for the encoder, but it's shifted right. So in today's video, I'd like to talk about specifically about encoder, which would be this one here, and these are the decoder. So what does encoder do? Like the main function of it. So it would extract. So it would transform these inputs into a format that that model would be understand deeply. Like it would extract these inputs into more meaningful. So it would still output same. It would so you are passing embeddings, and the encoder also outputs embedding, and these embeddings extracted or captured really meaningful inputs, meaningful information inside the inputs. I mean, they captured like dependencies between the tokens or the sentences, the words, and also it would processes simultaneously rather than sequentially, like one in conventional RNNs like LSTM, GRUs. Because of this multi-head attention layer, it would be able to capture long-ranged dependencies. So it would be able to capture longer sequences, longer sentences if the inputs were like text. And it's obviously faster because it would be processed simultaneously. Although I haven't, for my multi-head attention, it's not I'm not utilizing like parallelization yet. I need to add that system to my custom multi-head attention, but for famous machine learning libraries like TensorFlow or PyTorch, they definitely processes simultaneously. And also, this original transformer is encoder and decoder type model. They've got both encoder and decoder, but there is also encoder only and decoder only model. For encoder only model, the famous model is called BERT or Robert, and encoder only model is famously known as GPT, the one used for ChatGPT. And also encoder only models are used for like sentiment analysis task. So That's the main idea of encoder. So what's going to happen once we pass the input? So the input has passed and it would go to different places. First, it would go to this layer called multi-head attention, which enables simultaneous training processes, like I previously mentioned. And the input is used to create matrices called Q, K, and B inside this multi-head attention. I'm not going to talk about multi-head attention in this video, but yeah, input goes through this layer and it would output a tensors. And also input goes around kind of skipping the multi-head attention. This is called skip attention. This is the reason it has this kind of thing is to prevent vanishing gradient descent, because when you back propagate, like I haven't implemented back propagation yet for this model, but I assume when you back propagate from the final output, you'd have to back propagate back down to input, from output all the way to input. I think if you have this connection, you could skip this multi-head attention and just directly calculate gradients respect to this add and norm. I'm not really sure, but seems like one of the reason is so that it could avoid gradient descent. So anyway, this input would be added to output from this multi-head attention. That's what this add means. And this norm means normalization. So after you add the input and the output from this layer, you normalize it. And which would correspond to, in my code, it would correspond to here. So the input has passed to the encoder. I pass that input to first to this multi-head attention and also to this normalization layer. So input goes to two locations. And like I said, the output from multi-head attention. So I add the input to the encoder and the output from multi-head attention, and I normalize it. So we are up to here now, and now we have same kind of arrows. We just do the same thing, except instead of multi-head attention, we've got feed forward. But we do the same thing exactly like before. And we output the, meaningful embeddings, and we pass to the decoder in this example, like for encoder, decoder, model, but if it was encoder only, this would be the final output. Maybe you'd have like linear and softmax function in here. And this thing and the diagram corresponds to this one in my code. So since x1 is a tensor of shape 3D tensors, I need to use this slice function to slice into matrices. So just transform 3D into, I just take I just extract matrices from the tensor in order to, so this is the feed forward part, this for loop. It's just a linear transformation and use ReLU activation to introduce non-linearity. And I just add these result to this x2, which would be these 3D tensors, because it was in 2D, like matrices. And finally, I add the inputs to the x1 and the output from the feed for a neural network, which is x2. So this would be here in this diagram, add a norm. Yeah, and this is the normalization. Oh, and also I'm using post norm, but there's a pre-norm as well, meaning you'd normalize before passing to multi-head attention and feed forward, which would look like this. I think in original transformer it was post norm, so I used it post norm, but I don't know, I have to experiment to decide which one is better. I'm not really sure, but yeah, so I think for the next video I will talk about multi-head attention specifically. Yeah, thanks for sticking to the end of the video, and as always, thanks for all the supports. And yeah, thanks.